right. Looks like we're going. Check this out. And good morning, folks. How are we doing today? A little bit of optimal control in the morning. Think I'm muted. Yeah, I'm muted in Zoom. How about now? I'm not muted now. Can you hear me now? Good, better now. I hope so. I hope so. Anyway, hope we're doing great. Hope we're doing great. So today we're going to continue in our optimization part of the class. So a couple course notes. Expect the quiz to be released very shortly. We have the quiz designed. We're just going to release it on Canvas. Quizzes in this class are open note, open book, open. The idea is to make sure you're following along with the material outside of the homework, okay, with the concepts. All right, that's what we're looking to do. So with that, we're going to continue in the optimization part of the class. You know, there's an optimal control class. So we did a lot of control at the start in order to make sure that people had a little bit of background in control because they hadn't had it before. And we did that. You know, we were able to create dynamical systems. We were able to put controllers on a system. But we need to be able to design controllers. And the way we're going to design controllers is with various forms of optimization in this class. So last class, which was last week, I know we had Tuesday off because of the career fair. Hope you all have careers now, thanks to the career fair. So hope that was successful. Congratulations on all your careers. So, but last time we covered what we called linear programming, where we had this optimization problem that we set up. It was a linear optimization problem or linear program, and we solved it in MATLAB. That's what we did last class. And we showed that, hey, if you set up the problem as a linear program, you create the correct matrices and vectors, and you give it to MATLAB's linear programming solver, it will solve it for you. And because it is a convex program, meaning there are no nooks and crannies, that if you find the local optima, it's as good as the global optima. So it's actually very, very fast at finding the solution. Very reliable, okay? Which is good because we're going to need these reliable optimizations to optimize our controllers, okay? So last time we covered, so here today is the 12th of February, okay? We covered what we called linear programming, but that is not the only type of programming. And by the way, just as a reminder, what does program mean in the context of this course? What does it mean? What's a synonym for programming? Anybody? Anybody? That's important for this class because we will use the phrase program all the time. It doesn't mean computer program necessarily. It's an optimization problem is what it is. So a program is an optimization, okay? So here we're going to say, today we're going to cover quadratic programming. Now recall that a program, if you hear the word program, it just equals the word optimization in this class. And again, that is historical. There are historical reasons for that. Okay? So if you see programming here, that is the act of solving the program. So the program is equal to optimization. Programming is the act of solving an optimization. It'd be a lot cleaner if we just never used the word program, but it is just, it's baked into the cake of the literature and how people talk about it. Solving an optimization. And last time we covered a linear program, which was a linear optimization. Okay? So we're going to recall a linear program. Where we want you to solve an optimization. And thank you, by the way, for jumping in on it. I appreciate the answers to the questions in my ear. I can hear you. You can jump in on questions. I can hear you. My little hidden earbud underneath my voluminous hair. So, where our optimization problem, we're going to say a W star. This is our decision vector. That's the best decision vector. That's what the star means. That's the optimal. Okay? Is equal to the arg min, meaning we're looking for the minimum of some cost function. We'll call it f of w, subject to constraints. Oh, sorry. Okay, apologies. I'm going to get rid of the f of w. For the linear program, we said it was equal to c transpose w. This here is our cost function. Generally speaking, our cost function is just any old function of w, right? But for a linear program, the cost is linear. This is a linear cost. A linear cost. Okay? Subject to, that's what the ST stands for. That's subject to. Subject to the constraints that A, W is less than or equal to B. Okay? So these are linear constraints. Okay? That's what a linear program is. That's what we did last class. We set up an optimization problem. We said, you know what? That's a linear program. Why? Because a linear program has a linear cost and linear constraints. And specifically, we're going to say that our decision vector W is a bunch of real numbers. A vector of n real numbers. Okay? That's a linear program. Okay? That's what we set up last class. And then we went into MATLAB. And in MATLAB, we said, hey, MATLAB, friend, our buddy, if we give you C, which is our gradient, you'll recall, we give you A, which is our constraint Jacobian, as we call it. It's a matrix of constants, and B, which is a vector of constants. We give you C, A, and B, solve it. And MATLAB will solve it. Okay? Because a linear program, and it is basically guaranteed to solve it, basically, because a linear problem is convex. Okay? So linear programs are convex. Are convex, and thus reliable to solve with local optimization algorithms. Remember, they don't have any nooks or crannies to get caught in their cost function. If you're trying to do, if you have a cost function that looks like that has a bunch of wavy curves in it, if you're just trying to descend the curve until you hit the bottom. So if you imagine you have this is just a little thing off the side. Recall that this here is a local minima. This is also a local minima, but this is the global minima, right? So if we have an algorithm, its job is to descend the gradient and stop when it hits the bottom of a curve, which is where our first order necessary conditions, you'll recall from last week, okay? Then that's not the best solution. But if it's a convex problem, this is non-convex, this is convex, this is a parabola, then we know that if we use a local method to start here and look for a solution, we'll hit the bottom. It's convex, beautiful. We can use local solvers to get the answer. And that's the case for any linear program of this form. If we can put it in this form, it's a linear program, okay? But this program is restrictive, right? It means that we need a linear cost. Our cost function can only be a constant plus a decision variable plus another constant plus another decision variable. It's just written in this form. Any questions about that? That's what we covered last time. And we used it to optimize our grocery binge. we formulated an optimization problem, we turned it into a linear program, and we had MATLAB solve it. Now, because linear programs are kind of restrictive, can we have a less restrictive form that's also convex? And that's what the quadratic program is, okay? So here's the headline for types of programs, okay? Okay, give you a little chart, okay? Where here you're going to have your cost, you're going to have your constraints, and is it convex? Okay, this is the high level view. So if your cost is linear and your constraints are linear, what kind of program do we have? And I've said it 16 times already in this lecture, so you should know the answer. If you have a linear cost, you have linear constraints, you have a linear program, or LP. Or LP. Is it convex? Yes. That's great. Convex is good. Reliable to solve. We can give it to a solver. It almost doesn't matter what the initial guess is. It will still solve it. Sometimes you don't have to give it an initial guess. All right. Then you have, if you have a quadratic cost and you have linear constraints, that's what a quadratic program is. Or a QP. QPs are awesome. I use them all the time in modern control. They're incredible. We'll find all kinds of cool ways to turn a control problem into a quadratic program, and as a result, it'll run in milliseconds. So we can do all these kinds of crazy computations in order to control control robots or power plants or all kinds of things. Really crazy. Is it convex? Yes, if the Hessian is positive. Or positive definite, we would talk about in linear algebra, right? That means it's concave up. Hessian of the cost, okay? Okay. Now, there are a lot of different types of programs. I can give you a little bit of an outline of other kinds of programs that are neat. There's second order cone programs. There's sums of squares programs. They're all and semi-definite programs. There are all kinds of neat subclasses of programs that can be made convex. But for purposes of this class, we're going to be dealing with three types. There's the linear program. It's great. The quadratic program is awesome. We'll be using that a lot. And if things get more complicated, okay, if it's nonlinear cost or nonlinear constraints, if either or of those are nonlinear, we call it a nonlinear program. Or an LP. And to be clear, when I say nonlinear, in this case, it also means not quadratic. So like if it's quadratic and this is linear, oh, beautiful, it's a quadratic program, right? Okay. Common mistake, people think that a quadratic program means you have quadratic costs and quadratic constraints. Incorrect. That's a different type of program. It's called a quadratically constrained quadratic program. Not going to be dealing with that much in the class, or QCQP. Okay. But these are the main three. So in effect, if you have a nonlinear cost, it's also not quadratic, or you have a nonlinear constraints, it's a nonlinear program. Is it convex? We don't know offhand. You can do convex analysis, but for the purposes of this class, we don't know. okay? It could be, it could not be. You can do convex analysis to find out. But what it means is that we assume it's not for the purposes of this class. And we use solvers where hopefully comes up with a good answer, but we don't know if it's the best answer. We don't know. Okay. So those are the three types of programs. And we already covered a linear program, which is convex. Now, quadratic program. What does it look like? So quadratic program, I already covered that here. So now we have a quadratic program. Okay, in the general form, okay? W star. You're solving for the best decisions. That's your decision vector, right? It's equal to the argmin. Did I put a W down below? I apologize. Up here in linear program, I technically should put a little W right there. That's what we want to know. We want to know, hey, what's W, my guy? What's W? What's W? Okay. Of our cost function, and instead of being a general cost function of f of W, right? It's a quadratic cost function. 1/2 W transposed HW, okay? Plus a linear term, C transpose W. So here you have a quadratic term. And here you got your linear term. Okay, subject to the constraint. And our constraints, are they quadratic or are they linear for a quadratic program or QP? Put that in quotes, QP. What are they? Come on, not that early. Nobody? Linear, thank you. They're linear. And we can write those linear constraints as AW is less than or equal to B. Same exact form as our linear constraints from our linear program, right? So our linear constraints. Okay. That's a QP. That's what a quadratic program is, okay? And it is, so it's convex if H is greater than or zero, greater than 0, meaning it's definite, positive definite. Okay. Technically, it can be greater than or equal to 0 too. That works fine. So that's neat. So just like if we want to, so if we can take our optimization problem and we set it up so it's a quadratic program and it's positive definite, guess what? We can use MATLAB's or any number of existing quadratic programming solvers, okay? Quadratic QP solvers. And for linear programming, I'm just writing this out, it was called linprog, right? In MATLAB was the command. Linprog for linear programming. And in MATLAB, the command we would use to solve, in MATLAB with quadprog, right? And guess what quadprog has you give it? Okay? You give quadprog your A, your B, your H, and your C. That's all you got to give it, right? You can give it more things. There are more options, but that's the minimum, right? You can get away with that, right? So let's do an example, okay? Let's do an example. Let's solve the following optimization by writing it as a QP, quadratic program. Okay? Let's say we've got two variables, W, we got W1 and W2. They're real numbers, right? And I should say up here, I apologize, I'm going to scroll back up real quick and add that W is going to be, again, an element of real numbers. They are real valued elements of this vector, N. So we're not dealing with integers, as we've talked about many a time. Hopefully that's assumed at this point, but just for clarity. Okay? All I did was said, hey, they have to be real numbers in a vector for a decision. Hey, look, there's our decision vector. Okay? Sort of an abstract problem. I'm just going to give you functions here. Okay? So, and then our cost function be a simple cost function. We'll say f of w is equal to w1 squared plus 2w2 squared and plus 0.1 w1 times w2. Okay. And our constraints. We're going to have w1 plus w2 is greater than or equal to 1, and w2 is greater than or equal to 3. Now, that cost function is quadratic. And I'll show you how we know in this process. So we need to write this in a quadratic programming for it. It's quadratic. You can see these decision variables. They are squared, quadratic. Also, it works if you have one decision variable multiplied by another decision variable. Okay? It's still quadratic because it will still show up in this form. So what we have to find, we need to find H, C, A, and B. Okay. You'll notice that we're dealing almost exclusively with inequality constraints right now. It's not much different for equality constraints. Again, you can turn any equality constraint into two inequality constraints. So, but for convenience in MATLAB, or in so many of these solvers, you can just write in lots of different types of constraints to make it easier to write. We'll deal with that later, though. So we got to find H, C, A, and B. Okay. Now H, let's go back up a little bit. I'm sorry. That H, let's do a little different color here. That H, that's your Hessian of your cost, right? And that C, that's the gradient. Okay. And like with the linear programming, all of these matrices, H, C, A, and B, they're going to be filled with constants. Okay. They will be constants. If you don't get constants, it's not a QP. Constants with respect to decision variables, it's not a QP. All right, that's your hint. So if there are if you do all the math to compute your Hessian, your gradient, this A matrix for your constraint, which with the constraint Jacobian, and these constants, if you get a decision variable anywhere in those, it's not a QP, or you've made a math mistake somewhere. Okay, there you go. So decision vector. So back to this. So we need to find HC. Well, C C is the gradient. Okay? C is the gradient. H is your Hessian. Again, these are of the cost. Your A is your constraint Jacobian. And B are your constants. And if you're, for whatever reason, in the back of your mind are panicking about these fancy words, Hessian, gradient, Jacobian, they're all just partial derivatives. And we all know that partial derivatives are the easy derivatives. It's the easy derivatives. Okay. So let's take the partial derivative of our cost function f of w with respect to w. That is our gradient, right? We're doing it by hand, but didn't we cover last time in MATLAB how the symbolic toolbox can do it for us? Oh, how lovely. Oh, how great. Oh, how cool, right? Okay. All right. So that's going to be the partial derivative of, it's going to be partial f of w with respect to w1, partial f of w with respect to w2. Okay. Okay. And our cost function, where is it? Okay. So here's our cost function. The partial derivative of that cost function with respect to w1 is going to be, there's a w1 there, so it's going to be 2 times w1 plus 0.1 times w2. Two times w1 plus 0.1 times w2. Okay. And for the other, for this term right there, partial cost, partial w2, let's go back up. I see 2 times w2 squared, so take the derivative. That's going to be 2 times 2, so it's 4w2 plus 0.1 w1. Okay, that's going to be our gradient. Now, you might say, Christian, didn't you just say that, like, hey, look, there's decision variables in there. We screwed up. Okay, no, don't worry about it. Don't worry about it. We're gonna this is a waypoint on our way to on our way to excuse me on our way to our Hessian. Okay, so let's do our Hessian. Okay, our Hessian is going to be partial f squared. This second Hessian is just the second derivative, okay, which gives you this matrix, right? It's going to be a 2 by 2 because there's 2 decision variables. The Hessian is always square. Right? So it's going to be partial f of w squared, partial w1 squared. Then here's going to be partial squared f of w, partial w1, partial w2. This is going to be partial f of w, partial w2, partial w1. And here you're going to have your second derivative of w with respect to w2 squared. Recalling that along the diagonal, that's where you're going to have your w1 squared, w2 squared. If you had more decision variables, it would have w3 squared, all those w's, right? And then the off diagonals, you have the combinations, right? And because the partial with respect to w2 and then w1 is the same as w1 to w2, these two are going to be the same. It's going to be a symmetric matrix. Let's just fill this in. So you can see here that we've already taken the partial derivative of w with respect to w1 of the cost. So if we want this, we just take the partial derivative again of what we just took the derivative of. So partial w1, there you go. I only see one w1. So that means it's going to be the coefficient is 2. So the partial derivative of this with respect to w1 is 2. So the first entry is going to be 2. Now we need to take the partial derivative of the gradient here. that element with respect to W2. I see a 0.1, and that goes away, right? Follow me so far. We're doing the Hessian. We're doing the Hessian again. Okay. Now you can take a shortcut, and you know it's going to be symmetric, so you know that's going to be 0.1 on the other side. But just to check, if we take the partial derivative with respect to W2, which is right there, with respect to W1, hey, look, 0.1 times W1, 0.1. And finally, partial derivative of, with respect to W2, with respect to W2 again, there's the 4, voila. Hey, look, it has constants. Okay. If the Hessian has is full of constants, you're in good shape for a QP. Okay. Now, what about that linear term? Okay. What you want to do is substitute in for this gradient your decision variables where they equal to 0. Okay. So this extra term here, you scroll up, this captures things that aren't quadratic, that are linear. So if right now our linear cost here has, our cost here has a W1 squared plus 2W2 squared plus W1, W2. These are all quadratic terms. But if I had, for instance, a plus W1 in there, no other multiplication, that would show up in the cost, in the gradient of the cost. So C, where's C? So C is the gradient, but specifically, C is equal to the gradient of the cost with respect to your decision variables, where W equals 0. Meaning you substitute in zeros for all your decision variables. So that means that it's going to be 2 times 0 plus 0.1 times 0, 4 times 0 plus 0.1 times 0. So 2 times 0 plus 0.1 times 0, and 0.1 times 0 plus 4 times 0, which great scholars have contended equals 0. Okay? That's your C. Okay? Any questions so far? Okay. I'm listening. If you have a question, I just got to run and grab a tissue from the other room. Be right back. Okay. So we have our H matrix. We have our C matrix and our C vector. We're in good shape. Okay. Now let's get our A and our B. Now recall that our A is the partial derivative of our constraints G of W with respect to W. And because your constraints G of W is less than or equal to 0, this can be a vector. That means that thank you. No, you're good. You're fine. Good. I've been known to make mistakes. So you got that? Because G can be a vector valued function, W can be a vector. This means that this can be a Jacobian, right? This is a Jacobian. Again, just another way, just pairing together partial derivatives. That's all. Okay. All right. Okay. And that B was equal to minus G of 0. And the reason that was the minus g of 0 is because we are saying, hey, anything that's left over inside of g, we want to move to the other side and so it becomes a is less than or equal, AW is less than or equal to b. What we want. So that's what we covered last time. It's exactly like the linear program. We want to turn this general constraint, which is linear, into this form so we can give it to our solvers. Okay? All right, and we currently have two constraints. So g of w, So g of w needs to be less than or equal to 0. So what are our constraints? I'm going to scroll back up for a moment, pull up our constraints. Up. Here we go. W1 plus W2 is greater than or equal to 1. W2 is greater. I'm gonna write that down again. Okay, W1 plus W2 is greater than or equal to 1. And W2 is greater than or equal to 3. Is that what I said? Yes, thank you. W2 is less than or equal to, greater than or equal to 3. We got to put it into this form, which means we got to get everything into the less than or equal to 0 form. So let's move the constants to the other side. W1 plus W2 minus 1 is greater than or equal to 0. And W2 minus 3 is greater than or equal to 0. We're good with that math. We need, of course, to flip the inequality. So we have to multiply all these by minus 1, right? So that's going to give us minus 1 on both sides. So that's all kosher in terms of the math. Minus W1 minus W2 plus 1 is greater than or equal to 0. And, sorry, less than or equal to 0. Apologies. And minus W2 plus 3 is less than or equal to 0, right? Hey, now we have this function is less than or equal to 0. That means that if we say our g of w is equal to minus W1 minus W2 plus 1, then minus W2 plus 3, that is less than or equal to 0. Okay, we're great. Congratulations. We have our g of w. Now we can just figure out what A and B are. Where A is our Jacobian. We have two constraints and two decision variables. So this is going to be a 2 by 2 matrix. It does not have to be square, but this time it is square because we have two constraints. We have 2 rows equals 2 rows. And 2 decision variables, so it's going to be 2 columns. So when I'm playing a dangerous game, I'm boxing off my matrix before I draw it in, but you know, things I do for my students. So 2 decision variables. Equals 2 columns. Okay? So this here is going to be partial f, is going to be partial our first element of g, so we'll call it g1. So if we consider this g of w as being equal to some g1 of w and then g2 of w, basically all I'm saying is that g1 is the first one, g2 is the second one, right? That's g1, that's g2. We're cool with that. Let me just draw it out so you can see it. Call that g1. Call this g2. Right? So this is going to be, in the first row, it's going to be our first g1, partial our first decision variable, w1. This is going to be partial g1. Again, same row, so the top is the same, so g1. But we have a second column, so we change the bottom, so this is just the Jacobian. So that's partial w2. 1, 2. Then on this second row here, we're going to change our g1 into being g2. Partial g2, partial w1 is again first column, which means that we have the same w1s there. And partial g2, partial w2. Just so not everyone takes Jacobians every day, like me. So, great. Let's fill in those values. 2 by 2. So partial G1, partial W1, that's this right here. So I see a -1 times W1, so that's -1. There I've got partial G1, partial W2. I see W2 is just a -1 coefficient, so -1. And then I don't see a W1 in the second one, so it's going to be 0 there. And then minus GW2, that's -1. Okay. Hey, that's your A matrix. That's nifty, right? Okay. And B is just our G of W negative, what do we put up there? Sorry. Negative, but we plug in zeros for your decision variables. Okay. So B is going to be, B is going to be negative minus 0 plus 1, and then minus 0 plus 3, which is just the vector -1 and -3. That's B. Hey, there we go. Made a quadratic program. How hard was that? We have our H, we have our C, we have our A and our B. We can do our quadratic program. And guess what we'll bring up now? We'll bring up MATLAB. But before I bring up MATLAB, any questions so far? Okay, pop in at any time. All right, let's go to the board. So let's pull up MATLAB. So we might not even need to make a file for this. Okay, this might be pretty simple. So we're going to just try to solve this quadratic program. So if we want to use the quadratic programming solver, QuadProg. So you want to know how it works, you type help in QuadProg. And as it is with the very first thing you run in MATLAB when you start it up, it takes a little longer. Here we go. QuadProg, you can give it an H and an F. F is what we call C. That's our constant gradient vector, okay? Or we can give it constraints, A and B. And you can see where it defines these things. Where is it? Does it say where they are? Here we go. Here we go. Linear inequality constraints, real matrix, linear inequality constraints, real vector, etc. It's exactly as we said. That's the form we would be using with what we have, okay? Now, what if you had equality constraints? Like we've said many a time, you can take any equality constraint and turn it into two inequality constraints and therefore put it into A and B again, where A times W is less than or equal to B. We could do that. But everyone knows that's a little bit of a hassle. And when you have equality constraints, sometimes the math can be easier inside of the solver. So it will actually do an AEQ and BEQ matrix and vector respectively. You can put those in. And sometimes your constraints are simple enough where literally you're just trying to say that, hey, I want a decision value to be a decision vector variable to be above a certain value. I want a lower bound on it. We can define it there as a lower bound. That's what we have here, actually. You could consider this W2 is greater than or equal to 3. That's a lower bound on W. So they spared you a way to go through the rigmarole of putting that constraint in an A matrix. And you can say, hey, I want W2 to be greater than or equal to 3. So anyway, we'll get into those features later. But my point being is we're going to start with this form, where to give it Hessian, gradient, Jacobian over constraint matrix A and B for our linear inequality constraints. Okay. So let's define our various matrices and vectors. So here's H. So here's H. H is equal to 2, 0.1, semicolon 0.14. There's H. Now, is this a convex matrix? Is this a convex optimization problem? How do we check? We need to know if that matrix, if that Hessian is positive. Well, we can check by saying checking the eigenvalues of H. And look, the real components are all positive. And here's the thing, because it's a symmetric matrix, this is a linear algebra thing, there will never be any imaginary components of a symmetric matrix. So if these are positive, you're good. They're positive, they're good. right? Means that if we look at that cost, if we were to shape it in like space where you have decision variable in that direction, another decision variable in that direction, it's going to be a bowl where you can descend and hit the bottom. It's perfect, right? Now we're going to do our C matrix. It's just 0, 0. C vector, I'm sorry. The gradient, 0, 0. Done. Now our A matrix, we have there, -1, -1, semicolon 0, -1. Okay. There we go. And our B vector is right here. -1, semicolon, -3. Okay. There we go. H, C, A, B. So if we say quad prog, it gives you hints. You can give it the H. What we call C, they call F. The A matrix and the B matrix. Does it solve? Indeed. Minimums found that satisfies the constraints. That's good. It's telling you, the algorithm is telling you, hey, yeah, I found a minimum solution. Pretty cool, right? And there it is. There's the answer. The answer here is the first decision variable should be -0.15. The second decision variable should be 3. That's it. Okay. So, like I said, we can write this optimization program. We can write this in a couple of different ways where MATLAB will know how to solve it. Okay. We don't have any equality constraints, but we could add some. Okay. All right. We could add some equality constraints, for instance. Let's go back to here. Imagine we said, let's add equality constraints. So you could say, for instance, I'm just going to scroll up and take a look at my constraints here. Let's just say we knew that we wanted W2 to equal 5. Okay? That is one equality constraint. You could write this as some matrix A EQ for equality constraint times W is equal to B EQ. And you can see that, pull up the code again, real quick. It allows you to put in an AEQ and BEQ, and that's what that means right there. Okay? So, and you can compute the AEQ, EQ, and BEQ the same way we did for A and B, where A is the Jacobian, B is the leftover constants. Okay? So let's go back here. So we've got that. So we've AEQ, BEQ. So if this is our only equality constraint, we could say that we can frame that as being some GEQ as being equal to 0. And then AEQ is now the Jacobian of that constraint with respect to your decision variables, W, partial GEQ, W with respect to W. And BEQ is equal to minus GEQ of 0. Okay? So we have one equality constraint. So W2 is equal to 5, that one right there. Okay? That means that our Jacobian is going to have one row. But we still have two decision variables, W1 and W2. So we're going to have two columns. We got to make sure that we know what, so GEQ has to equal 0. Equals 0. So we're going to, in order to make this constraint equal 0, we just subtract both sides by 5. So GEQ is equal to W2 minus 5, and therefore equals 0. Look at all the wizardry and math we're doing. Okay, not that hard, right? So let's take the partial derivative of GEQ, which is right there, with respect to, it's going to be partial G, partial W1, partial G, partial W2. Just for my own carpal tunnel, I'm just omitting the of W. Actually, I'll include it. I wasted so much time even saying that. I'll just include it there, right? Okay, that's your Jacobian. It's a 1 by 2. Right? So that's going to end up being partial derivative of this with respect to W1, no W1s. There is, however, a W2 with coefficient of 1. Boom, boom. And BEQ is this function. But we plug in zeros for our decision variable, so that's 0. So this becomes -5, and we take the negative, so it's +5. Right? So if we added this AEQ here and BEQ there, this should guarantee that the result will have the second decision variable, W2, must equal 5 in the optimization. Let's go back to the optimization here. All right. Okay, so we're going to set AEQ equal to 0 and 1. 0 and 1 as a row vector, so 1 by 2 matrix, I should say. And let's say that BEQ is just the number 5, right? That's what that is right there. So now we can do the same quadratic programming solve where it will say quad prog H F. We still have the same inequality matrices A and inequality vector B for the linear constraints. AEQ and BEQ are now things we've defined, okay? Let's add those. Run. What happens? Oh, sorry, not FC. I apologize. Thank you. What I get for having a slightly different convention. Hey, look. Our second decision vector, after it's solved, it found the minimum that satisfies the constraints, literally what we're asking for in optimization. W2 is 5. W1 is -0.25. Okay? So we can add equality constraints, and you can do that for linear programming too. The same deal. And finally, you have the little lower bounds. So if you look at quad prog again, there's all kinds of things you can add here. You add a lower bound and an upper bound. And each of these, what these are vectors that allow you, that if you put them in, they will literally say this decision variable cannot be higher or lower than the upper and lower bound respectively. So for instance, if we go back to our original problem, okay, so back to our original problem, back to our original constraints. Original constraints were 1 plus greater than 2. Yeah. We had W1 plus W2 is greater than or equal to 1. And W3 must be greater than or equal to W2, sorry, must be greater than or equal to 3. Right? This here that's a bound. It's a lower bound. It cannot go lower than 3, right? So we could write it as a lower bound. We don't have any bound on W1. We only have this linear constraint that the combination of W1 plus W2 must be greater than or equal to 1. Because it's a combination of these two values, it has to show up in your A matrix. There's no way getting around it. But we could put this as a bound. So where we can take a bound. Okay. And that means we can take it out of the other inequality constraints. So now our inequality constraints, our A matrix, can just be equal to the partial derivative of just this one constraint, which we had to put on the other side. What is it, like minus W1 minus W2 plus 1 is less than or equal to 0, right? That's our one constraint. So now we'll have one constraint and two decision variables in our for our A matrix. That means we have a 1 by 2 Jacobian. So we can, if we move this into being a bound and not an inequality constraint for the A matrix, this is now just a 1 by 2. So this would be partial G1, partial W1, partial G2, partial W2. Okay. So partial G, that's -1. And -1. We've done that before, right? And the B matrix is going to be -1. Is that what we decided? That what B was? To be clear, it's the same. Oh, sorry. I'll make it bigger for you. I apologize. Make it bigger. Got to change the viewpoint. Yeah. No, just B. Yeah, -1. So you'll notice that our B matrix, let's go back to here. Apologies. Our B matrix just eliminates, because we got rid of the second constraint from the inequality constraints, we just eliminated that -3. And if we look at A, we just eliminated that second row. So it's just -1, -1. Okay? We got rid of the constraint. We got rid of the row. Cool, right? So now we can make our lower bound. What we want to define for our lower bounds, we know our lower bound we want to be 3 for our second decision variable, right? What's our lower bound for the first decision variable? Well, we don't have one, okay? And the way that you would tell that to MATLAB is you have to say, I want my lower bound to be -infinity. Okay? That's what you would tell it. And your upper bounds, we don't have any upper bounds. If we don't have upper bounds, we would tell it we want our upper bounds to be +infinity. In MATLAB, you just say INF. Okay? So what we can do is go back to MATLAB. We can remake our A matrix. We're going to go back to our original problem with no equality constraints. We're going to get rid of the equality constraints. Our A matrix is now -1, -1. We got rid of the second row because we got rid of the second constraint. B is now just -1. We got rid of the second row because we got rid of the second constraint in A. Oh, so that's 10. Sorry. Okay, -1. Okay, now we got to make some lower bound LB. And so it's going to be a vector of the same size of our decision vector. That's what we have right here, right? We have a 2 by 1. The lower bound in our first decision variable is -infinity. So open bracket, minus INF, semicolon, 3. MATLAB understands what infinity is. It's got rules for that. Why do we have a G2? Where's the question? What G2 do you see? Cricket. Did I say G? Oh, I meant to say G2. That would be G1. That's just a typo, Cricket. Apologies. Good catch. Good catch. Thank you. All right. Okay, we've got that. We've got UB, and our upper bounds are just 2 infinities, right? Positive infinity. There is no, the sky is the limit for these variables. Infinity, semicolon, infinity for both variables. So we put it like that. Yeah. All right. So now we have an upper bound and a lower bound. Okay. So let's do our quad prog again, and it will return. Yeah. Yeah, it's made positive. Yeah, I'm typo. Thank you very much. Boom. All right. Should be positive. Thank you. I think that was Marco. All right. So we got quad prog. We're going to give it our Hessian, give it our C, give it our A and B, our new A and B, A matrix and B vector. Okay. I want to take off the equality constraint I just added. That if I want to take that off here, where is it? Oh, I no longer want W2 equal to 5. I just get rid of my equality constraints, but you still got to put something here in order to get to the later arguments of you can see it's because we have to get to the lower bound upper bound. So if I hit, let's just say I just put the number 1 and 1, don't do this, but you can see, oh, now it allows you to do lower bound upper bounds, right, for those two. So you got to put something there. So you have nothing for those constraints or any constraints or anything you want to add. All you got to do is open close bracket. That tells you don't have anything. It's a 0. It's a size 0 matrix. Okay. So you have no equality constraints now. I took them off. I want them gone. So I get rid of AEQ and BEQ. They're both open close brackets. That's what you do. Now you have lower bound. Now you have upper bound. This X0 is if you want to add an initial guess. For a quadratic program, you generally don't have to because it's convex, but you can. It might make it solve faster, but you don't have to. Okay, let's start with that. There you go. Same solution we had before, but we just put one of the constraints as being a lower bound. Questions about that? So now we know how to use these optimization algorithms within MATLAB. We got to give it information. This H and this C, that's information about the cost. This A and this B, that's information about the linear constraints and any equality constraints and any lower bounds and upper bounds, okay? You'll notice that there are also options that you can add to the optimization. You can change the algorithm. You can have it display. So let's add quadprog. Oh, let's go to help quadprog. You can add options. All right. If you want to add options, you want to use the optimization option structure optim options. And I'll show you what that is real quick. Okay. For instance, like how is this even solving the optimization problem? Well, there's a lot going on behind the scenes that you don't see when it's solving. What it's doing is it's starting with a guess of what the answer it is, and then it iterates, and tries to get closer until it finds an answer. So let's go to, let's go back to our old, so let's create an options structure. So options is equal to optim options. You can give it a, you can tell it what solver you want to, what solver we want to work with. We're working with quad prog. Okay, and what options do we want? One thing I like to do is change the display. Okay, and change the display to iter. Okay. Sometimes I like to do this to see if for some reason my optimization is not working, you know, what could be going wrong. I create this optimization structure here. Okay. So there we go. And it creates this option structure. And if I give this structure to quadprog, it will have a new set properties where it displays the iterations of each step. So I'll show you what that looks like. So if we do the same quadprog, we give it H, we give it C, we give it A, we give it B, no equality constraints. So no AEQ, no BEQ, give it lower bound, give it upper bound. We have to give it X0 now. That's annoying. So what I'm going to do is going to give it initial guess. This is basically asking you, hey, what should I start with for a guess for my solution? You have two decision variables. So I'm going to say, start them both as zeros. 0s, 2, 1. I'm just going to start at zeros. This really shouldn't matter. And then give it the options. Okay, I'll go scroll up and show you what I typed here. Where is it? Where is it? It is right. Here it is. There you go. That's what I typed. Okay. That's what I typed. And look what all popped out here. Okay. This is the algorithm working. Okay. We changed the display setting so it's displaying each of the iterations of the solver. We've not coded our own solvers yet for these algorithms, but we'll do some. Okay. This will get your what we're doing today will get your feet wet and be able to know how to use these solvers for homework. Okay. But how to code them yourselves, the way they work is you take an initial guess of what you think the best answer is, and then it tries to improve it until it says it can't get any better. And so what happens is it says, hey, how feasible is my solution? Okay. No, I don't want that. Thank you. So what I mean by that is that if I gave it an initial guess, if I said, hey, the guess of the solution that I want, I'll write it over here. So let's you have a guess. And I just arbitrarily said, hey, what if W is 0 and 0? Is that the solution? The answer is no. We know the answer is not 0 and 0. Here's the question. Is it even feasible? The answer is no, because for one, W2 is not greater than 3. It's not feasible. Okay? And so this number here, on the very first iteration, it's saying, actually, it's off by like 3. And also, this is off as well. I'll point out. Like there are two constraints. It's like W2 plus W1 has to be greater than or equal to 1. These two constraints are off. This tells you how far you are off in your constraints. Okay? Right? And notice with each iteration, it tries to get better. By get better, meaning it gets closer and closer to 0. Look at that. 10 to the minus 7th, 10 to the minus 10th, 10 to the minus 14th. That's a tiny value. As it gets closer and closer to 0, the closer and closer it is to getting a solution that is what we call feasible. Okay? Now here, this dual infeasibility, this is telling us basically, more or less, how close we are to not just a feasible solution that satisfies the constraints. That's what this does. This tells you how close you are to the minimum of the cost function. Okay? So in order to solve any of these optimization problems with any of these algorithms, somewhere behind the scenes, there's a feasibility number and an optimality number that is trying to drive closer and closer to 0. And here, this is mega close to 0. 10 to the minus 14th, right? That's what it's doing. Okay. Now, for quad prog, this is less important because quad prog is so good, it's often you can just set it and forget it. If quad prog doesn't solve, it's probably your fault. It's probably set it up wrong. Okay. It might not be a quadratic program. It might not be a feasible quadratic program. I'll tell you what I mean. Let's go back to our AEQ, BEQ, our AEQ and BEQ for our equality constraints. We said that, hey, if we have equality constraints, let's set W2 is equal to 5. What if we said W2 must be equal to 0? Well, that would be bad because we've also told it that W3 must be greater than 3. And because 0 is not greater than 3, it's impossible. We can give it an impossible problem. So the way we can do that is we say, hey, if BEQ is equal instead of 5 to 0, now we're going to make W2 equal to 0. So let's try that again with quad prog. Let's run quad prog, but this time we'll put our equality constraints back in. So we're going to say our Hessian, our gradient, we call it C, A and B are still the same. We put back in our AEQ and BEQ. They're not just open and closed brackets. They're not empty matrices. LB, UB, zeros, 2, 1, and let's look at the options. Okay? That'll add the iteration. So, okay. Okay. The problem is infeasible. We gave it an impossible problem, and it knew it wasn't feasible. Okay? Right? So the answer is it doesn't give us an answer. And to be clear, this function is returning the optimal value, right? So if I turned off the inequality constraints of this, if I turn them back into the equality constraints into just being open and closed bracket, I can just store them in some W, right? That'll give me the answer. As in W. Okay. That's how we use the optimization packages within MATLAB, right? We just got to give it in the right form. If it's a quadratic program, you got to give it its Hessian. Got to give it its gradient, right? Any questions? All right. So here we did all of our Hessians and gradients by hand. We don't need to do it by hand. Okay? Using the MATLAB symbolic toolbox, we can do the same tricks we did last time. So if we want to know what the Hessian is of a cost function, well, let's do this. Let's go back to our Hessian of let's go back to our cost function. We can find out what the Hessian of our cost is. Where's our cost? There it is. Okay. We can create symbolic variables W1 and W2. Oh, that should be W2. Sorry. I'll fix it. W2. This creates symbolic variables W1, W2. Let me clear out everything because I kind of screwed up on that. So W1, W2. I can create a vector of these symbolic variables W1 and W2. Voila, right? I can create a cost function F. That's this thing right here. Is equal to W1 squared plus 2 times W2 squared plus 0.1 times W1 times W2, right? Okay. I can say, hey, my friends, what is the Hessian of F with respect to W? I'm glad you asked. There we go. You'll notice that it is currently in a fractional form. So where's our answer, right? See, exactly the same thing. It's clearly still a symbol because it's doing these fractional forms. So if you want to cast it as the answer, you could say, hey, I want h to be the doubled form, meaning like I turn into a floating point value of the answer that I just got. Voila, there's h. Okay? And now our gradient, our c vector is equal to the gradient, but we substitute in 0 for w, right? So what we can say is we can say that c is equal to the gradient of our cost f with respect to w, but you'll notice that there are decision variables in there. We have to then substitute in zeros for our decision vectors. So what we can say is I want c to be equal to minus. Again, we need to, no, we don't need minus. Forget I said anything. We want it equal to the substitution. We'll substitute wherever there was in c. Wherever there was a w, we want to substitute in a vector of zeros. We have 2 zeros. There you go. Voila, 0, 0. These are current. This is still a symbolic class object. We don't want that, so we say c is equal to double c. Done. Make sense? Same exact process that we did for the linear program, right? So we can have MATLAB figure out those matrices for us. We give them to we give them to the quadratic programming solver, and it solves, right? And this was a sort of an abstract program. Let me go back to the thing. So this program I just set up, this optimization problem, I just gave you a cost. It looks like that, right? And there are now quadratic terms in it. Okay, why is this so important for a lot of the control elements of this class? Why is the quadratics important? Well, a lot of our costs are going to be quadratic in control. Okay, so in control, problems, we often have quadratic costs. Okay. So we have quadratic costs. So for instance, imagine you have a robot arm. Okay. Looks like this. Got a little gripper on the end. Okay. You have a robot arm. You apply a torque at this motor here. We'll call it torque 1. Torque at that motor, torque 2. A lot of times the cost function might be tau 1 squared plus tau 2 squared. By minimizing the square of the torque, it's saying, hey, I prefer to not give much torque to my robot. I want to be efficient, right? There are other components of cost as well, all right? Or errors. Cost, you have efficiency. You can also have cost in terms of error. So if you have some state that you want to go to, x desired minus x of t squared, that's an error, right? That you want to drive to 0. And by squaring it, that's a state. Squared cost is important, okay? So quadratic programs show up all the time in control. Okay. Your next homework is going to make sure that you know how to set up optimization problems and solve them in MATLAB. Okay. We will be using linear and quadratic programming to start, but MATLAB also has nonlinear programming capabilities. Just pull up MATLAB just before we leave. Okay. For nonlinear programming, there's a great function called fmincon, which stands for minimizing a function subject to constraints, okay? And you'll see a lot of similarities to what we just saw. Hey, look, an A and a B matrix. Those are your linear inequality constraints. AEQ, BEQ, those are your linear equality constraints. LB and UB, those are your bounds, okay? The only thing that's different is it gives you the capability to have a cost function that can be nonlinear. And non-LCon, that's a constraint function that's nonlinear. Nonlinear, non-L, constraint, okay? That's the key difference. And in that world, when you're using f-min-con, you may have no guarantee the problem is convex. At which point, it's much more important, or likely to be more important, what your initial guess is. Your guess at what the best solution is. And that's what x0 is. Okay. We threw that in as a throwaway into the quad prog because it didn't matter. They were going to figure it out. Okay. But here it matters more in nonlinear programming. Okay. Here, find the minimum of a constrained nonlinear multivariable function. Okay. That's what we got for today. Any questions before we finish up? Okay. All right. With that, thank you all for, yeah, question. Question is, can you optimize your choosing of initial conditions? Theoretically, yes. And that would be an but to know if it's a good initial condition or not, if you were trying to optimize it, that means you would have an optimizer around your optimizer. And people do that. People do bi-level optimization, they call it, right? And but one thing we're going to find in this class is that if you are smart about setting up your optimization problem right, even if it's nonlinear, you can have pretty terrible initial guesses and it will still work. All right. So yeah, so what we're all thrusting toward with this class. So like we have optimization now. We have control. We're going to put those together, and the way they're going to come together is what we call trajectory optimization. And you can review last year's lectures if you want to get a jump ahead, or of course the reading material on trajectory optimization. But there are different ways to set up the problem where it's like almost miraculously robust to bad initial guesses, and it'll come up with a good solution. Thank you for your question. All right, folks, thanks for stopping by.